Okay, so basically before the Big Bang, and you gotta watch how you say that. If you're super clear that the Big Bang is when the universe got crazy hot and dense, and we can actually see evidence of that, then our best guess is that there was a time before that called inflation. What was there before the Big Bang? I know scientists have been scratching their heads about this forever, but it sounds like they might have an answer now, and Brian Cox says it's kind of scary. So picture this. The universe was just there, cold and empty, but expanding like super fast. Then that expansion slowed down and stopped, and all the energy that was powering it just got dumped into space, heated everything up, and made all the particles that we're made of. Boom, that's the Big Bang. So what freaks scientists out about what came before? Well, there's this idea called eternal inflation, which says that inflation never really stops. It just kind of stops in little pockets, and imagine the universe stretching and stretching, and then slowing down in these little spots. Each of those spots is basically its own Big Bang and its own universe. So, you end up with this picture of a never-ending, fractal-like universe with tons of Big Bangs. That's the inflationary multiverse. It's hard to imagine absolute nothingness, right? Even if you took all the energy out of the universe, it still wouldn't be truly empty. Right now, the universe is crammed with matter, radiation, antimatter, neutrinos, dark matter, and dark energy. And even without energy, the universe can still make new energy. It's mind-boggling. It's like the universe doesn't get what empty means. Even an empty universe would still be expanding and making radiation. The Big Bang is a bit of a misunderstanding. This goes way back before the hot Big Bang. It seems the universe never completely empties out. So, could the universe have come from nothing? It looks like there's always something there. Even if you remove all the particles and stuff, there's still empty space. If you get rid of all outside fields, you still have quantum fields and the basic laws of physics. There's always some energy there called zero-point energy. That's about as close to nothing as you can get in our universe. You might think of something even more nothing-like, but it's not realistic. You can't recreate it in an experiment. Science tells us that something always exists because true nothingness doesn't work in our universe. But why? Science hasn't answered that one yet. Our universe is far from empty right now. It's full of stars, gas, dust, galaxies, and all sorts of radiation. And with better tools, we might find even more stuff like gravitational waves, dark matter signals, and different kinds of black holes. Everything we see is in a universe that's always changing. It's interesting to see how it all evolves. Space itself is expanding. 2 points far apart get farther apart over time, and light traveling between them stretches out. The universe is getting bigger and colder. During this expansion, things with mass attract each other and form clusters, making a huge cosmic web. If you could take everything away, all the matter and energy, you'd still have empty space expanding, following the laws of physics and filled with quantum fields. That's the closest you can get to true nothingness. But it still follows physical rules. To a physicist, taking away anything else would be unrealistic. That means dark energy would still be there, even in a universe with nothing else. Was there a previous universe? If every quantum field was at its lowest energy, you'd get to the zero-point energy of space, where you can't get any more energy out. If the universe has dark energy, it's likely that the zero-point energy isn't actually zero. As the universe expands and cools, radiation will eventually take over, but dark energy will be the main thing. Also, there was a time way back when cosmic inflation happened before the hot Big Bang, when the universe expanded super fast. Instead of matter and radiation, the universe was controlled by the energy of inflation. It's like dark energy today, but much stronger and faster. If eternal inflation is true, but time is limited, where did the universe come from? There has to be a start somewhere, right? To really get into it, let's talk about 3 things that often get mixed up: the hot Big Bang, cosmic inflation, and whether the universe had a beginning. Inflation and the Big Bang might not fully answer that last question. Back in the early 1900s, some important stuff happened. Alexander Friedman showed that, according to Einstein, a universe with matter and energy can't stay still. It has to expand or contract. Henrietta Leavitt figured out how to measure the brightness of stars. Vesto Slipher saw that galaxies were moving away from us really fast. And Edwin Hubble found similar stars and figured out how far away those galaxies were, confirming they were far beyond our own. All of this led to the idea of an expanding universe. If the universe widens, space stretches, and the stuff in it gets less dense. Light stretches out too, so the universe cools down. If you go backward in time, everything gets denser and hotter. If you go back as far as physics allows, you'd get to a point where everything was squeezed into a single point of infinite density and temperature. The cyclic universe theory. The initial Big Bang idea led to 5 predictions about the early universe. The universe should be expanding. It should have been pretty uniform at first, with things like stars and galaxies forming later. It used to be too hot for atoms to form, which led to the discovery of the cosmic microwave background. It was also hot enough to create light elements like hydrogen and helium, and neutrinos played a big part too, which has been confirmed recently. With all this evidence, the Big Bang theory has been the main explanation for the early universe since the 1960s. But as more proof came in, some problems popped up that the Big Bang alone couldn't solve. Some stuff didn't fit with the idea of the universe starting from a super hot and dense state. 3 things stood out. Asterisk the horizon problem. Asterisk the universe has the same temperature and density everywhere we look, even in places that never had a chance to interact and reach the same temperature. Asterisk the flatness problem. Asterisk the universe is perfectly balanced between expanding and collapsing, making it spatially flat. Why? Asterisk the monopole problem. Asterisk if the universe was super hot and energetic early on, why don't we see exotic particles like right-handed neutrinos and magnetic monopoles? Instead of just accepting these problems, scientists looked for a way to explain them. Alan Guth came up with a solution in 1980. Maybe there was a period of superfast expansion called inflation, where the universe's energy was in space itself, not just in particles. Inflation could solve all those problems. It could explain why the universe has a uniform temperature because everything was connected in the past. It could explain why the universe looks flat because inflation stretched it out so much. And it could explain why we don't see those exotic particles because inflation prevented the universe from getting too hot. In the 1980s, inflation theory made some testable predictions about the start of cosmic structure, specifically about the cosmic microwave background and the layout of the universe. Even without energy, the universe still makes new energy. It's like the universe doesn't understand what empty means. If you took away all the energy, you'd think it would go to absolute zero with no particles, but that's not what happens. Even in empty space, the expansion of the universe would still make radiation. The Big Bang is actually a misunderstanding. This goes way back before the Big Bang. The universe never really becomes nothing. So, could the universe have come from nothing in the first place? It seems like something is always there. Even if you get rid of all the particles, there's still empty space. If you move away from everything and block all outside forces, there's still a kind of emptiness, but quantum fields and the laws of physics are still there. There's always some energy in that space. That's the closest we get to nothing in our universe. You might imagine something even more empty, but it's not realistic. No experiment could make that happen. Science tells us that something always exists because true nothingness can't exist here. But why that is, science can't answer yet. Right now, our universe is definitely not empty. It's packed with stars, gas, galaxies, and radiation. And with better tools, we might find even more stuff like gravitational waves and signals from dark matter. Everything we see is happening in a universe that's always changing. It's interesting to think about how the universe changes on a huge scale. Space is expanding, which means the distance between 2 points gets bigger over time. The universe is not only getting bigger, it's also getting colder. Light stretches out, so it has less energy and lower temperatures. It used to be hotter, and it will get colder in the future. Things with mass or energy pull on each other, forming big groups and making a huge network in space. If you could somehow remove everything matter, energy, all that would be left is empty space, still expanding, still following the laws of physics, and still with quantum fields. That's the closest we get to true nothingness. But it's still something. To a scientist, getting rid of even that would create something that doesn't exist in our world. It also suggests that dark energy would be there no matter what. Was there another universe before ours? Basically, if all the quantum fields were at their lowest energy, we'd get to the zero-point energy of space. If there's dark energy, it's possible that zero-point energy wouldn't really be zero. As the universe expands and cools, there will be a time when radiation is strongest, and dark energy will be the main thing affecting everything. But there was also a time in the past when something other than matter and radiation was in charge. During cosmic inflation, the universe expanded super fast. It wasn't matter and radiation that were doing it, but the field energy of inflation. It was like dark energy, but way stronger and faster. If inflation is always happening, but time is limited, where did the universe come from? There has to be a beginning, right? To really get into that, we need to talk about three things: the hot Big Bang, cosmic inflation, and whether there was a true beginning to everything. Back in the early 1900s, some big ideas came together. Alexander Friedman showed that a universe filled with matter and energy can't stay still. It has to expand or contract. Henrietta Leavitt figured out how to measure the brightness of stars. Vesto Slipher saw that galaxies were moving away from us really fast. And Edwin Hubble, with Milton Humason, measured the distances to those galaxies and saw that they were far away. All of this led to the idea that the universe is expanding. If the universe expands, then space stretches and the stuff in it becomes less dense. As space expands, radiation stretches, causing the universe to cool. If you go backward in time, the opposite happens. The universe gets denser and hotter. If you go back as far as possible, you'd get to a point where all matter and radiation were in a single point of infinite density and temperature. This is called the cyclic universe theory. The Big Bang theory led to 5 main ideas about the early universe. 1. The universe should be expanding. 2. It should have been pretty uniform at first. 3. It used to be too hot for atoms to form. 4. It should have created light elements like hydrogen and helium. 5. Neutrinos should have played a big part. These ideas have been proven with evidence, so the Big Bang theory has been the main explanation for the early universe since the 1960s. But as more evidence came in, some issues popped up that the Big Bang couldn't explain on its own. Some observations didn't match the idea of the universe starting from a single superhot point. 3 problems stood out. Asterisk the horizon problem. Asterisk the universe has the same temperature and density everywhere, even in places that never had a chance to interact. How did they get to be the same? Asterisk the flatness problem. Asterisk the universe is perfectly balanced between expansion and gravity, resulting in a flat universe. Why? Asterisk the monopole problem. Asterisk if the universe was super hot early on, why don't we see exotic particles like magnetic monopoles? Instead of just accepting these problems, scientists looked for an explanation. In 1980, Alan Guth came up with a solution. Inflation, a period of rapid expansion where the energy wasn't in particles but in space itself. So, instead of taking these conditions as simply the way things were, which goes against the scientific method, scientists tried to find a mechanism to set up those starting conditions. Alan Guth proposed a solution to these mysteries in 1980 with a groundbreaking paper. He suggested that an early phase of rapid expansion, where the universe's energy wasn't spread among matter and radiation particles but was instead intrinsic to space itself, could solve all 3 issues. Guth said that an early phase of rapid expansion where the universe's energy wasn't spread among matter and radiation particles, but was part of space itself, could fix these problems. Asterisk horizon problem. Asterisk the universe used to be connected, but inflation stretched that connection out, making it look uniform now. Asterisk flatness problem. Asterisk inflation made the universe so big that it looks flat, like a small patch on a balloon. Asterisk monopole problem. Asterisk inflation kept the universe from getting too hot, so those weird particles never formed. In the 1980s, inflation theory made specific predictions about the beginnings of cosmic structure that should be visible in the cosmic microwave background and the large-scale layout of the universe. These predictions have been confirmed by observations since the 1990s. There's a limit to how hot the universe could have gotten during the hot Big Bang.